All right, so today we're diving into something kind of really cool.
Yeah.
We're talking about quantum dots and, those tiny nanocrystals that are already, like, shaking things up, like, in our TVs,
Exactly.
solar panels and stuff.
Yeah.
Well, get this. Researchers have just figured out how to fine-tune them
Yeah.
using something that we encounter every single day, light.
It's really remarkable.
Light. So
Yeah.
wild.
And what's so fascinating is that this ability of quantum dots to emit color in such a unique way. It's not like pigments or dyes or anything like that.
Right.
They all comes down to their size
Oh, wow.
and how that affects their energy level.
So it's not about what they're made of, but how big they are.
Exactly.
Oh, that's interesting.
Yeah.
Tell me more about how that works.
So think of it like this. Each quantum dot
Okay.
has a band gap.
Okay.
It's essentially a specific amount of energy
Okay.
that's needed to bump an electron to a higher energy level.
Okay.
And when that electron falls back down, it releases light.
Okay.
And the smaller the dot, the larger the band gap.
Uh-huh.
And the more energetic the light it emits,
Okay.
pushing it towards the blue end of the spectrum.
Okay.
Larger dots emit lower energy redder light.
Okay, so changing the size of the quantum dot changes the color.
Exactly.
Okay, so how did scientists control that size before?
Yeah.
I'm guessing it wasn't as simple as grabbing tiny tweezers?
No, not at all. It was far from simple.
Yeah.
Traditionally, they've used chemical modifications or high temperature reaction.
Right.
It's a bit like trying to bake a cake.
Yeah.
You need the right ingredients and the right oven temperature
Yeah.
to get the color and consistency you want.
Yeah. But I bet those methods have some downsides, right?
They do.
Especially if we're talking about mass production.
Yeah, exactly. Those older methods can be pretty energy intensive
Right.
and sometimes inconsistent as well.
Yeah.
It's hard to control the exact size of every single quantum dot,
Right.
which can then affect the purity and brightness of the color.
That makes sense. So where does light come into play here?
Right.
It's not like shining a flashlight on something is going to magically shrink it
No.
and change its color.
No, you're right.
Yeah.
But it can trigger some pretty amazing chemical reactions.
Really?
Yeah, so researchers at North Carolina State University
Okay.
found a way to use light to directly manipulate the band gap of perovskite quantum dots.
Perovskite quantum dots?
Yeah,
That sounds pretty high-tech.
they are.
What are those exactly?
So they're a class of materials that have shown huge potential in fields like solar energy
Oh, wow.
and LEDs.
Okay.
For this research, they started with perovskite quantum dots that emitted green light.
Okay.
And these dots were put into a solution containing either chlorine or iodine.
Chlorine and iodine,
Right
like
there.
the stuff we use for pools and first aid.
Exactly.
What do those have to do with color?
Well, it's fascinating how everyday substances
Yeah.
can play a totally different role in cutting-edge research.
Right.
They're not disinfecting anything here.
Okay.
This solution flows through a microfluidic system,
Okay.
essentially tiny channels etched onto a chip,
Wow.
which has a light source built in.
Okay, so we've got tiny dots flowing through tiny channels,
Yeah,
bathed in light.
bathed in light.
What happens next? How does this light actually change the color?
So this is where it gets really exciting.
Okay.
When the light hits the solution containing chlorine,
Mm-hmm.
it triggers a reaction
Okay.
that shifts the perovskite quantum dots color towards blue.
Okay.
With iodine, the shift is towards red.
So by choosing chlorine or iodine and controlling the light,
Exactly.
they can fine-tune the color they want.
Yes.
It's like having a high-tech color mixing palette.
It is.
Wow.
And what's remarkable is the speed and precision.
Yeah.
The microfluidic setup ensures that the light penetrates the
Wow.
entire solution evenly,
Okay.
making the color change incredibly uniform and
Oh,
fast.
so fast.
Yeah, we're talking about fine-tuning the color in a fraction of the time it used to take.
I can already see the wheels turning for our listeners.
Yes.
But before we get carried away with the possibilities,
Yeah.
let's break down how this new method actually works
Okay.
at a deeper level.
Sounds good. So it all boils down to how light interacts with the atoms in those perovskite quantum dots.
Okay.
You see, when light hits a material, it can be absorbed or reflected or transmitted.
Right.
In this case, the energy from the light
Okay.
causes the chlorine or iodine to interact with the perovskite structure.
Okay.
And this, in turn, changes the spacing between the atoms,
Wow.
essentially tweaking the size of the quantum dot.
So it's like the light is acting like a tiny sculptor,
Exactly.
subtly reshaping the quantum dot to emit a different color.
It's a remarkable level of control.
Yeah, that's wild. I'm starting to understand why scientists are so excited about this.
Yeah,
But let's shift gears a bit
sure.
and talk about why you, the listener, should care about this.
Right?
Imagine the possibilities if we could harness this level of precision
Yeah,
in everyday technology. I
absolutely.
was just thinking about that. Displays immediately come to mind.
Yeah.
Could this be the key to even brighter, more vibrant screens on our phones and TVs?
Mhm.
No more washed out colors.
Yeah, and because this method is so precise,
Right.
we could see displays that dynamically adjust their color temperature.
Oh, wow.
Imagine your phone screen subtly shifting to warmer tones in the evening
Okay.
to reduce eye strain.
That would be amazing.
Yeah.
But beyond just visuals, couldn't this revolutionize lighting as well?
Your spot on LEDs are already incredibly energy efficient,
Right.
but this takes things to a whole new level.
Yeah.
Imagine LEDs that shift their color throughout the day,
Okay.
mimicking natural sunlight.
Right.
They could boost our focus during the day
Uh-huh.
and then transition to a calming, warm glow in the evening.
It's like having a personalized lighting system that syncs with our natural rhythms.
Exactly.
I can see this being huge for homes, offices, even schools.
Absolutely. And don't forget about the potential impact on greenhouses.
Oh, yeah.
We could use this technology to give plants the exact wavelengths of light they need to thrive.
Wow.
Talk about maximizing crop yields and potentially addressing global food security.
Okay, now we're talking about solutions with a real impact.
Yeah.
This isn't just about making things look prettier. It's about addressing some big challenges.
Exactly.
What about solar energy?
Right.
I know quantum dots are already being used in solar panels,
Yeah.
but could this new technique boost their efficiency?
That's one of the most exciting prospects. Yeah. Traditional solar panels can only capture a limited range of sunlight spectrum.
Right.
But by using light-tuned quantum dots,
Okay.
we could design solar cells that absorb a much broader range of wavelengths.
So we're talking about harnessing more of the sun's energy.
Exactly.
That could be a game changer for renewable energy.
It could.
Wow.
Imagine solar panels that adapt to different weather conditions and times of day,
Yeah.
capturing energy even on cloudy days
Wow.
or at dawn and dusk.
It sounds almost too good to be true, but I have to ask.
Yeah,
Are there any potential downsides we need to consider?
you're absolutely right.
Every new technology comes with its own set of challenges.
Of course, one of the biggest hurdles will be scaling up this process from the lab to mass production.
Right.
It's one thing to fine-tune quantum dots in a controlled setting,
Yeah.
but manufacturing them on a large scale while maintaining that precision
Yeah.
will be a significant engineering challenge.
So we shouldn't expect to see light-tuned quantum dot TVs on store shelves next week.
Probably not next week,
Okay.
but I'm optimistic about the future.
Okay.
Another consideration is the long-term stability of these light-tuned quantum dots.
Right.
We need to be sure they maintain their desired color and performance over years of use.
Yeah.
More research is needed to ensure their durability.
Reliability is key for any technology to become mainstream.
Absolutely.
What about the environmental impact?
Right.
I know you mentioned that this light-driven approach is generally more sustainable than traditional methods.
Yeah.
But are there any concerns about the manufacturing process?
That's a crucial point. While using light to tune quantum dots is cleaner than using harsh chemicals or high temperatures,
Right.
we still need to assess the environmental impact of producing these specialized perovskite materials
Okay.
and the energy required for the entire process.
It sounds like a classic balancing act,
Yeah.
weighing the potential benefits against any potential risks.
Exactly. Responsible innovation requires careful consideration of the entire life cycle of a technology,
Right.
from raw materials to manufacturing to disposal.
So while we've painted a pretty optimistic picture,
Yeah.
it's important to remember that this technology is still in its early stages.
Yes.
We need to be cautious, but also excited about the possibilities.
Definitely.
It feels like we're on the cusp of a new era in materials science, wouldn't you say?
Absolutely. This research is a perfect example of how seemingly unrelated fields like chemistry, optics, and nanotechnology
Yeah.
can converge to create something truly groundbreaking.
Yeah.
It highlights the incredible power of light, not just to illuminate, but to fundamentally alter and control the world around us.
I think our listeners are starting to grasp the magnitude of this discovery.
Yeah,
It's not just about prettier colors, it's about a paradigm shift in how we interact with and manipulate matter.
it is.
But before we get too philosophical, let's bring it back down to earth for a moment.
Okay.
What are some of the immediate next steps for researchers working with this light-driven technique? So we've covered a lot of ground from the,
We have.
nitty-gritty of band gaps to the potential of these light-powered quantum dots
Yeah.
to revolutionize everything from our screens to solar energy, even agriculture.
Yeah, it's amazing.
So what are some of the key areas
Yeah.
that researchers are focusing on right now?
Well, one of the big challenges, as we mentioned earlier, is scalability.
Right.
Finding ways to manufacture these light-tuned quantum dots
Mm-hmm.
efficiently and cost-effectively is crucial if we want to see them
Yeah.
in widespread use.
Right.
So researchers are exploring different techniques like roll-to-roll processing.
Roll-to-roll processing.
Yeah, it's similar to how newspapers are printed
Wow.
to produce large quantities of quantum dots.
So instead of tiny chips and microfluidics, we're talking about industrial scale production.
Exactly, it is. And it requires innovation, not just in chemistry, but also in engineering and materials, science.
Wow.
Another area of focus is fine-tuning the light sources used in the process.
Okay.
Different wavelengths of light can trigger different reactions
Right.
and produce different color shifts.
Okay.
So finding the optimal light recipe for each application is key.
It's like we're not just controlling matter with light, we're conducting an orchestra of light and matter.
That's a great analogy.
Yeah.
And of course, long-term stability is crucial.
Right.
Researchers are investigating ways to encapsulate
Okay.
these light-tuned quantum dots
Okay.
in protective shells similar to how delicate electronic components are shielded
Yeah.
to ensure they maintain their color and performance over time.
So it sounds like there's a lot of exciting work ahead.
Oh, definitely.
And it's going to take collaboration across different scientific disciplines
Absolutely.
to bring this technology to its full potential.
Yes.
But I think our listeners are starting to get a sense of just how transformative this discovery could be.
Yeah.
It's not just about incremental improvements. It's about opening up entirely new avenues for controlling matter with light.
And it's a beautiful example of how fundamental research,
Right.
driven by pure scientific curiosity,
Yeah.
can lead to unexpected breakthroughs with real-world applications.
Right.
Who would have thought that shining a light on tiny dots
Yeah.
could unlock such profound possibilities?
It reminds us that the most groundbreaking discoveries often come from exploring the seemingly mundane with fresh eyes and a sense of wonder.
Absolutely.
So as we wrap up this deep dive, I
Yeah.
want to leave our listener with a final thought.
Okay?
We've talked about how this light-driven technique could revolutionize displays lighting solar energy, even agriculture.
Mm-hmm.
But what other properties of matter might we be able to manipulate with light in the future?
That's a great question.
Could we control electrical conductivity,
Yeah.
magnetism, or even the very shape of objects
Yeah.
simply by shining the right kind of light on them?
It's a question worth pondering. We're only just beginning to understand
Right.
the intricate dance between light and matter.
Yeah.
And as we delve deeper, who knows what other astonishing secrets we'll uncover.
Wow.
The future is literally bright.
It is.
And it's limited only by our imagination and our willingness to explore.
So to our listener, we say this: keep your eyes open, your mind curious,
Yes,
and never underestimate the power of a simple beam of light.
absolutely.
Until next time, keep exploring.